In this video, we continue our discussion of Chapter 3, Experimental Error and Uncertainty in Measurements, as we prepare for class number 7. So a little bit about what we're going to be covering. We're going to be looking at sections 3.4 and 3.5, which is about how we propagate uncertainty. So remember, uncertainty is now that plus or minus error bar that we have on a particular number. So if we're doing calculations with those numbers, which we often do in analytical chemistry, we ask the question, well, what is the plus or minus uncertainty that we get in the final result? And so to do that, we have to propagate that number through our calculations. And then we're going to learn something about the real rule for significant figures, and then how we propagate systematic uncertainties. So this is going to get pretty mathy, so as Harry Potter said on the night bus, strap yourself in because it might be a bumpy ride. All right, so propagating uncertainties and random errors. For most experiments, we need to perform arithmetic operations on several numbers, right? So most of the times when we do an experiment, we will have measured volumes, we'll have measured some masses, and we're going to take all those and do some calculations with those. Typically, we'll just be multiplying, dividing, adding, and subtracting, that kind of thing. But we would like to know each measured value has an uncertainty. What's the uncertainty in the final result, say the molarity of a particular solution? So we want to know what is the plus or minus value, that uncertainty, in that calculated result. So it turns out that the most likely uncertainty is not the sum of the individual uncertainties, right? So you might guess, just as a first guess, that, well, you just add up all of the uncertainties and get the total uncertainty. But because some of them sometimes might be a little bit higher than the true answer, some might be a little bit lower than the true answer, because that's the nature of random error, we would expect some of those errors to cancel, right? So some of the ones that are a little bit positive, a little bit higher, and some of the ones that are a little bit negative, they're going to cancel each other out. So it turns out that we can answer this question mathematically, how we do that. And it turns out that you need calculus to figure out how to do that. But lucky for us, people that know calculus have figured out the equations for us, so we don't need to worry about where they came from mathematically. We can just use the equations once they're given to us. So let's take a look at some of those. So propagation of uncertainties. So it depends on what mathematical operation you're doing. So this first equation that we're going to use is when we're doing addition and subtraction. So if you want to propagate the uncertainty through a calculation where you've done addition or subtraction, we're going to use this formula. And this is when we have random errors. So we've eliminated the systematic error, and all of our uncertainty is just due to random error. So E then stands for error. That's our uncertainty. 3 is some calculated value, so value number 3, right? And to calculate that, we have added or subtracted two other measured values, 1 and 2. And each one of those measured values has an uncertainty, so E for the error there. And that uncertainty would be that plus or minus. So we're going to drop the plus or minus and just plug the absolute number in there. So basically it says take the uncertainty in measurement number 1 and square that. And then add that to the measurement, the uncertainty of the measurement in measurement number 2, and square that. Add those together, and then take the square root of that whole mess. Now, if you've got more than 2 numbers that you've added and subtracted together, you just expand this bit underneath the radical sign here. So we'd have plus E, well, this is E3 here, but plus E3 squared plus E4 squared, and so on, and then E whatever, 5 or 6 or whatever, would be our final result. Okay, so you can just expand this easily. And this is the same formula whether it's addition or subtraction. So you don't change this mathematical sign here to a minus sign if it's subtraction. So you use the same formula whether you're adding or whether you're subtracting. So these errors right here, we call those absolute uncertainties. And in the next slide, I'll talk a little bit more about specifically what those are. So with multiplication and division, we use a different formula, which uses something called the relative uncertainty. And this formula actually uses the percent relative uncertainty. So if you're multiplying and dividing two numbers, you're going to take their uncertainty and calculate their percent relative uncertainty. And I'll show you how to do that in the next slide, so don't panic. And then what we're going to do is take those percent relative uncertainties, square them, add them together, and then take the square root of that number, and that will give us the uncertainty in our multiplied or divided result. And technically, I should fix this. This is going to be the percent relative uncertainty in 3. So you should, if you're taking notes on this right now, write a percent sign right here. So percent E3. So that will be again, relative uncertainty. So what if you're doing something, a mathematical operation, other than adding, subtracting, or multiplying and dividing? Now that's mostly what we do in analytical chemistry, but a few times we'll have to take logarithms and that kind of stuff. Well, there are other rules for propagation of random error found in table 3-1 in your textbook. And here is that table. So here are those rules for addition and subtraction, multiplication and division. Remember that the rule for addition and subtraction, it's the same formula, right? Same for multiplication and division, it's the same formula, except we're using percent relative uncertainties, and we're calculating a percent relative uncertainty instead of an absolute uncertainty. And here's some other functions. So let's say y is our calculated number, x is our measured value, and we're raising it to some power a. So this is the formula that you would use to calculate it. So you're going to get the percent relative uncertainty in y, and that's going to be equal to whatever a is times the percent uncertainty in x, which is your measured value. What if you get y by taking the logarithm of some measured value x? Well, we can figure out the absolute uncertainty in y by taking this formula, and this number right here is basically an approximation to 1 over the natural logarithm of 10, and so out to 5 decimal places, it's 0.43429. Then we're going to multiply that by the absolute uncertainty in x. X is our measured value, and then we're going to divide it by x, the actual measured value. Okay, so this thing right here is actually what we call a relative uncertainty, which I'll talk about in the next slide. But anyway, you get the idea. Here's some other formulas of common things that we might use when we're calculating relative uncertainties. Now what we want to look at is kind of that difference between absolute and relative uncertainty. So absolute uncertainty is what we've already been talking about, okay? So nothing new there. It's just the uncertainty. I say AKA, it's that plus or minus error bar number that we've been looking at. So plus or minus 0.02, plus or minus 0.007, plus or minus 1, whatever it happens to be in the measured value. And the uncertainties will have the same units as the measured value. So if you measure a volume on a burette to be 21.43 milliliters with an uncertainty of plus or minus 0.02, that plus or minus 0.02 has units of milliliters, right? So you're uncertain by 2/100ths of a milliliter. Your reading might be 2/100ths higher, might be 2/100ths lower. So that's your uncertainty. Relative uncertainty, though, is a ratio of that uncertainty, the plus or minus error bar, to the measured value. And it is a unitless quantity because the units on the uncertainty and the units on the measured value will cancel out in that ratio. So we define it this way. So relative uncertainty is equal to, oh, by the way, we're going to use the symbol often, E sub y. So E just stands for the error or uncertainty, and y is standing for whatever quantity, whatever measured value. Temperature, volume, milliliters of something, right? So whatever measured quantity you're looking at, mass. So relative uncertainty then is going to be the absolute uncertainty, EY, that we just talked about, divided by the measured value. So the units will cancel out, and you'll get just a fraction, a number. Okay, so EY is the absolute uncertainty, and Y is the measured value. So for example, let's say we measured a length. So we measured a length in centimeters, 24.3, and we estimate or calculate in some way that our uncertainty, our absolute uncertainty, is plus or minus 0.2. So this number right here is our absolute uncertainty, and it has a value of 0.2. Both of these have units of centimeters, so 24.3 centimeters, and our absolute uncertainty is 0.2 centimeters. So to calculate the relative uncertainty in this number, we're going to take the uncertainty, 0.2, and divide that by the measured value, 24.3. And then we get this fraction, 0.0082, without units. So it is a unitless quantity. Often we will express this as percent relative uncertainty. So basically we're just going to convert this fraction into a percentage in the usual way by multiplying by 100. So this is the same fraction that we saw before. We're just going to multiply by 100 to convert it into a percentage. So just as an example, from up here, we have our 0.2 divided by 24.3 times 100. So multiplying this number by 100 gets you 0.82%. So that's our percent relative uncertainty. So we have an uncertainty in this number, 24.3, of plus or minus 0.82%, which turns out is plus or minus 0.2. All right, so why do we use these different ones? Well, they show up in these formulas, and that's why we're going to use them. But relative uncertainties are actually useful in their own right because they let us compare the uncertainties in different measurements. So maybe we have two measurements that are on vastly different size samples, or perhaps we're trying to compare a measurement of mass to a measurement of volume where the units are even different. So if we compare their relative uncertainties, then we can say something about which measurement is the more precise measurement. Remember, precision is about reproducibility. So your smallest amount of uncertainty means your results have more digits in them, right? So let's just talk about maybe we measured the mass of something, right? And so we measured the mass of something and we've determined that our uncertainty was plus or minus 0.2 grams, all right? So then we measure the mass of something else, and we decide that our uncertainty is plus or minus 2 whole grams, right? So which one gives us better precision? Well, you might think it's the 0.2 grams, but it really depends on what we're weighing, right? So if we're weighing a paper clip that's going to have a mass of about 1 gram, then plus or minus 0.2 is in the tenths place there in that gram unit. And so that's really not great precision, right? So we're measuring something that's like 1.1 grams plus or minus 0.2 grams. That's not great. But if we're measuring the mass of an elephant, so the mass of an elephant is going to have a mass of about 5 million grams, right? So an uncertainty of 2 grams compared to that 5 million grams is really great precision. We've got a lot of digits there, right? So a lot of digits there. So if we're comparing really big size. So if we compare the percent uncertainties in those two measurements, you'll see that the one that has the smallest percent relative uncertainty is our most precise measurement. And so we can compare measurement to measurement by using percent relative uncertainty and figure out which measurement is the most precise. So that's a really useful tool. We'll be doing that in labs a lot. I'll be asking you which measurement was the most precise. And for that, you'll calculate the percent relative uncertainty and tell me which one is smallest. So now we're ready to move on to what I call the real rule of significant figures. And then after that, we're going to do some examples of these kind of calculations, okay? So significant figure rules, we've been talking about those in Gen Chem when we've just reviewed them. But, you know, following Captain Barbosa here, we need to recognize that those, quote, rules are really more like guidelines. You know, they help you most of the time represent a number at the end of the calculation without misrepresenting the precision, right? So you're reporting it to a number of digits that accurately reflects the precision that you expect. But now we're able to do a better job. So our real rule of significant figures will tell us that the first uncertain digit, so the first digit, the first place, whether it's the ones place, the tenths, the hundredths, the thousandths, or whatever, that first digit is going to be our last significant figure. So this is always the right way to report significant figures. But to do that, we're going to have to propagate the uncertainty. So let's pause this video for a second and move over to the Blackboard, and I'm going to work out some examples for you. So you'll probably want to copy these down in your notes as I'm working through them to get an idea of how to do some of these calculations. So in this propagation of error example, we're going to use the addition and subtraction rule. So we're going to think about what is the uncertainty in volume delivered by a burette. So you'll remember when we have a burette, like here, what we do is we take an initial reading at whatever our volume is, then we're going to open the stopcock and make sure that there are no air bubbles in their tip, and we're going to drain some of the solution out of the burette. So we're going to take an initial reading, right? Then we drain some volume out, and then we're going to take a final reading, call V subscript F for final, and then the volume delivered, which I'll call V sub D, is just the difference between those. VF minus VI will tell you how much volume you squirted out into your beaker or whatever receiver container you have here. So let's try to estimate the uncertainty in a single reading. So let's say we're looking at this over here on our left side as our reading. Okay, so this is one of our initial or final volumes, let's say. And we've got this handy little black card. So this has a white background, but then there's a black line, a dark black line that's right here. And if we bring that up behind the burette and get it kind of close to the meniscus, at some point the meniscus right here will start to reflect that black line, and it really helps it pop in our eye. And so you want to hold your eye so that it is level with the meniscus, and we're going to try to read this. So I'm going to read this and see what number I think we get. So here's 34, so this is 34.1, 0.2, 0.3, and 0.4. So it's between 34.3 and 34.4. So we're going to call it 34.3. And then I have to estimate between the lines here. So it looks like the bottom of the meniscus right down here is more than halfway, right? So I'm going to call it, but it's really hard to tell, but maybe it's 8, right? So 34.38 milliliters. So this is the way you should read your burettes. Always report it to the hundredths place because you can read in between the lines. So I realize this is kind of blown up. That it seems like those markings are much closer together when you're looking at an actual burette. Anyway, so we need to estimate what is our uncertainty. So this was our uncertain digit, right? Because we're certain it's a 30, we're certain it's 4, we're certain it's at least 0.3 milliliters, so it's somewhere in between there. So we're uncertain in this digit. How wrong could we be, do we guess? Well, maybe it's as high as 34.34, right? Maybe it's right on this line, but it doesn't look like it's quite there. And maybe it's as small as 34.36, which would make it look more like it's halfway in between these two lines, but I don't think it's quite that far. So I'm just going to estimate that our uncertainty, our absolute uncertainty, is plus or minus 0.02 milliliters. So that's just based on how far off I think I could be in recording this particular value. And it's just an estimate, so that's okay. But you see in doing this formula that I'm going to have to make 2 readings, and each one of those may have some random error associated with it. So what would be the random error associated with the final volume? Well, let's use our formula to calculate that. So we've got an uncertainty in the initial measurement, right? That's plus or minus 0.02, and so that's an absolute uncertainty. We've got an uncertainty in our final measurement. Same number, right? So we're going to have an equal chance of reading the burette incorrectly there. And so we want to know what is the uncertainty in the volume delivered. So I'll just use D for delivered there. And so our formula tells us that it is the square root of E1, or E sub I in this case, squared, plus E sub F squared. So now we just need to plug numbers in. So we have 0.02 is our uncertainty in the initial measurement. That's going to get squared. We're going to add that to 0.02 squared, and then we're going to take the square root of that. So you want to carefully punch that into your calculator. So what I do is I type in 0.02, and then somewhere on my calculator I have an x squared function, so I'm going to hit that. And then I'm going to type the plus sign right here, and then I'm going to type in 0.02 again and that x squared function, and then I'm going to go ahead and hit the equals sign. And then to take the square root, I'm going to hit the square root function. So for me, I have to hit a second key to get that square root function up. And then I'm going to use my previous answer. So you could type that in, but on my calculator, I have a second answer, ANS function. And so that'll just put my most recent result in as the answer. So I'm going to quickly come in and do that. So I type 0.02, square that, plus 0.02, square that, equals, and then I get a number, 8 times 10 to the negative 4th, and I'm going to take the square root of that. So second square root, second ANS, equals, and I get a number that is 0.028. All right, and there are more digits than that. And again, this is a volume measurement, so this is going to have units. It's an absolute uncertainty of milliliters. So we're going to round this to the first uncertain digit right there. So this is approximately equal to an uncertainty of plus or minus 0.03 milliliters. So even though your uncertainty in an individual reading is plus or minus 0.02, because we measure the delivered volume with 2 measurements, our uncertainty is a bit higher, and we've propagated that uncertainty through the calculation, so it turns out to be plus or minus 0.03. So our volume delivered, we subtract the 2 volumes, and maybe we get 22.06, and then our absolute uncertainty is plus or minus 0.03 milliliters. And that's how we might represent that, so that somebody can look at the number and tell, well, how far off could they be? Well, by 3 in that last digit, plus or minus. Okay, excellent. So now let's go and look at a multiplication division example. So in this example, we want to measure the density. And so to measure the density of something, we need to measure its volume and we measure its mass. So let's say we're trying to measure the density of a liquid, and so what we can do is pipette very precisely 5 milliliters of volume into a beaker that we've tared, and then we can weigh the mass. So let's say that the volume is equal to our 5 milliliters. And because we've done many trials with this 5 milliliter pipette, we've been able to calculate a standard deviation in that pipette, and this is just the random error associated with us trying to get the meniscus in the right place and so forth, and maybe it's 0.007 milliliters. Okay, so there's our volume, and then we've measured the mass. So we measured the mass on our balance, and let's say our mass for this liquid is 3.9327, and that's going to be in grams. And since we're using those analytical balances, they actually read to better than plus or minus 1 in this last digit. They read to plus or minus 0.00005 grams. So that's our uncertainty. So it's half a decimal place further than our actual reading. So this is our high precision balance. And so we want to know, well, what is the uncertainty in the calculated density? So density is mass divided by volume, right? So we could calculate it 3.9327 grams in every 5 milliliters of volume that we pipetted over. And so that will give us this number, 0.78654 grams. And we want to know, what is the uncertainty in this value? So we're going to have to propagate that. And so our propagation of error formula is going to let us calculate the percent uncertainty in the density, and that's going to be the percent uncertainty in the mass squared plus the percent uncertainty in the volume, V, squared, and then we're going to take the square root of all of that. So let's figure out what those numbers are. So you'll remember to calculate the percent relative uncertainty in some quantity y. We take the absolute uncertainty and we divide it by the measured value. So here inside my parentheses, to get the percent relative uncertainty in the mass, that's going to be 0.00005, right? Lots of zeros there. We're going to divide that by the mass measurement, which is 3.9327. So both of these have gram units, and that'll cancel out. We will multiply that by 100 to make it a percent, and then we need to square all that. So I'm going to put it in square brackets just so we can keep track of all this. That gets squared. And then to that we're going to add, there's our plus sign right there, we're going to calculate the percent relative uncertainty in the volume. And so again, that's going to be our uncertainty in volume, which is plus or minus 0.007. And then we're going to divide that by the volume measurement, which is 5 milliliters, 5.000. Both have units of milliliters, and so the milliliters will cancel out. We multiply this by 100 to convert it into a percentage, and then we square that. And then after we squared that and added those together, we're going to take the square root of this whole mess. All right, so there we go. So now we need to carefully put that in here. And so what I'm going to do is calculate these percentages first, and then I'm going to go through in a couple of steps and do that. So let's get some numbers here. So calculate that first percent relative uncertainty. So now we get these two percentages, 0.01966% and 0.14%. So one thing you can immediately see is that the precision of our mass value is much better. So we have a much smaller number here, than we do for the volume measurement. So of these two measurements, the volume measurement is the least precise. So if we wanted to have a more precise measurement of density, we would need to somehow figure out a better job of how to do a better job with the volume measurement, how to make it more precise, more reproducible. So just comparing these percentages, that's how we can figure that out. So probably when we do this square root business, we're going to get an answer that's going to be pretty close to this. But let's go ahead and do that. So we're going to square each number, add them together, and then take the square root of all of that. Okay, when we're all done, I got a number that is, like I said, close to that 0.14. So 0.1414%. All right, so including some extra decimal places, we'll sort out how many decimal places to report in just a minute. All right, so now I've counted the percent relative uncertainty in the density. So then we know that the density is 0.78654, now plus or minus 0.01414%, right? But we would like to know the absolute uncertainty, so we've got one more step that we need to go through. Oh, by the way, you should check and make sure that you're getting the same numbers that I am in your calculator. If not, maybe tinker around and see what you're doing so that you can get the same numbers that I'm getting. If not, please come and talk to me so we can sort out what's going on with your calculator. Okay, so now we need to figure out the absolute uncertainty in density. And you'll remember that the percent relative uncertainty in density is going to be the absolute uncertainty in the density divided by the density volume. So we can rearrange this equation to solve for the absolute uncertainty, and it's just going to be the density value times the percent relative uncertainty. Oops, times 100. That's an important bit. So times 100 to get the percentage. And so it's going to be the density times the percent relative uncertainty divided by 100. And so we know what all those values are. The density is 0.78654 grams per milliliter. The percentage is 0.1414. I just figured that out. And then we're going to divide that by 100. And so when we're done, we get this number, 0.0011111. There's several ones there. Okay, and so now that's going to have the same units as density, so that'll be grams per milliliter. So now we have accomplished our goal. We have figured out what the density is. So the density is equal to 0.78654. Now, if we look at this number right here, our uncertainty, you see that our first uncertain digit occurs in the thousandths place. So we are going to use our real rule for significant figures and only report our density out to the thousandths place, because once we get to the thousandths place, we start becoming uncertain in what the value of that digit is. So our first uncertain digit becomes our last significant figure. So we don't have to worry about these significant figure rules. We let the uncertainty tell us where it should be. So that's going to be that number, 86. Let's see, did I round it correctly? Okay, so it's 8654. And because this number is greater than 5, we're actually going to round up. So I'm going to change this 6. Let's erase that. We're going to round it up to a 7. 0.787 plus or minus 0.001 grams per milliliter. There we go. So now we've got it expressed with its absolute uncertainty right here. So we've got an uncertainty of 1 in that last digit, but we actually calculated that by propagating the error through that. So I realize that that's quite a grind, but take it step by step. Each individual step, not too bad. I realize that there's a lot of math there, so you have to first calculate all these percentages, right? Plug those in, square those, add them, take the square root. So, a lot of mathy kind of stuff going on here. And even then, you're not done, because you might want the absolute uncertainty instead of the percent relative uncertainty. So then you have to go back and use this last formula to go from percent relative uncertainty to absolute uncertainty. All right, so that's an example of how we do that. Now that we've gotten some practice propagating error through arithmetic calculations, let's look at a different kind of propagation of error. This is the propagation of systematic error. The formulas that we were looking at before are good for propagating random error. So remember, the difference, one difference at least, between systematic error and random error is that systematic error is always in the same direction. So it's not sometimes below and sometimes above. So when you're combining errors from different sources, they may not necessarily cancel each other out. So systematic error occurs in some common situations in chemistry. So when we're calculating molar mass, molecular mass, and when we're looking at volumetric glassware calculations. So as I pointed out, it's treated differently from random error. And for systematic uncertainty, what we do when we're adding and subtracting, when that's our arithmetic operation, so this applies just for sums and differences. So what we do is we add the uncertainties together, as long as it's from the same quantity, okay? If they're independent quantities, then we do something different. And I'll explain that in a minute. So let's say that we have the systematic error on the mass of some atom. We're trying to calculate the molar mass, which is made up of n atoms of that element. So the uncertainty in the mass of that element is going to be n times the uncertainty in the mass of one of those atoms. So if you had several atoms, n atoms, then the total uncertainty is going to be n times. Basically, we add the uncertainty of each atom together. The uncertainty of atom 1 plus the uncertainty of atom 2, and so on. So we get a bigger uncertainty that way. So uncertainty in the mass of a molecule that has several different elements is computed by propagating the systematic uncertainty for each element as you did before. And that's because the uncertainty in hydrogen, let's say, will be different than the uncertainty in oxygen. So those are independent of each other. And so then you might start to get some of that cancellation and error that we talked about. And so then you'll use the normal propagation of error formulas. So let's do an example, and hopefully that'll help make this a little bit more clear. I realize this may seem a little bit confusing right now. This is a copy of the periodic table from the inside cover of your textbook. So this is one half of it because it spreads onto 2 pages, but so that it's not too small, I just copied one half of it. So what you see here for the molar masses, again, these are the average molar masses averaged over the isotopic distribution of those different isotopes on Earth. So, maybe it's 30% of this, 30% of this other isotope, and we average those together to create a weighted average. So this number right here is then that weighted average, and then there's a little plus or minus next to it. So this is the uncertainty in the last digit. So nitrogen, for example, 14.0068. Notice the space here is just to help your eyes see the groups of 3, but it goes all together. So 14.0068 plus or minus 4 in this last digit. So here we've got for fluorine plus or minus 5 in this last digit, but it's got a lot of precision, 18.9984032 with plus or minus 5 in this last digit. Okay, so pay attention to that. Now, these uncertainties are not random errors, so it turns out that we can measure these fairly precisely. But the reason that there's some uncertainty is that the isotopic distribution of these elements is not the same everywhere you are on Earth. So some places, like here in Illinois, we might get some oxygen atoms, say from water that we've pulled out of a well that's connected to an aquifer deep in the ground. And the isotopic distribution of oxygen in that water sample might be different from the isotopic distribution of water that we get from an ice core that we've drilled out of an ice sheet in Antarctica. Okay, even though they're both water, they're both oxygen, there may be differences in those isotopic distributions. In fact, there's some interesting things about those isotopic distributions, in particular the distribution of the isotopes for oxygen in ice or water give you some idea, and even in things that build molecules out of water like plant tissue, give you some idea of the temperature at that time. So we can use isotopic ratios of oxygen to actually serve as a proxy for temperatures way back in the past. That's how we know something about what the climate was like long ago before humans started recording temperatures. So because of that, it might mean that the average mass of the oxygen that you're using in your particular sample of water is systematically higher. So that water that you get from the aquifer here in Illinois, the average mass of oxygen will always be systematically higher than, say, the average mass of water that you get from some other source, some different place on the planet. So what's the range of that variation? Well, it's plus or minus 4 in this last digit. So at most, the average mass of the oxygen in your particular sample, wherever you're getting your sample from, could be 4 units higher or 4 units lower in this last digit. So these are all systematic errors. So if we're trying to calculate the molar mass using these uncertainties in this table, then we will need to propagate the systematic uncertainty. Okay, let's look at an example. So let's say we want to calculate the uncertainty in the molecular mass of O2. So that's made up of 2 oxygen atoms. So the average molar mass of oxygen is somewhere in the range 15.9984 plus or minus 4 in this last digit. So that particular sample of oxygen that we get that makes up this O2 may be systematically high, systematically low, depending on where on the planet we get it. So the uncertainty in the mass is going to be the uncertainty of one atom, which is this number, times the number of atoms. So in this molecule, we have 2 oxygen atoms, so our uncertainty is plus or minus 0.0008, which is what we get when we multiply 2 times this uncertainty. The way we would use the propagation of error formula that we saw before, if this were random error, we would take 0.0004 and square it and add it to 0.0004 squared and take the square root of that, and we would get this number, 0.0005, and the next digit would be a 6. It's not significant, but we're just showing you what that next digit would be. So you see that this uncertainty is less than the systematic uncertainty. And that's because in this case, we get some of that lucky cancellation and error. But if we're systematically high, we're always high in the same direction. So if you have 2 oxygen atoms and they're both off by 0.4 high, you could be off by this much, right? 0.0004 high, excuse me. You could be off by as much as 0.0008. Right? So that would give us the uncertainty in our molar mass of oxygen. Let's do an example of propagating systematic error when we're calculating the molecular mass of a formula. So what's the uncertainty in the molar mass of H2SO4? That's the molecule that when dissolved in water would give us sulfuric acid. So the first thing we're going to do is propagate the systematic uncertainty in the hydrogen and the oxygen, since those are the atoms that we have more than one of. So hydrogen, we have 2 of those atoms in H2SO4, and the uncertainty in the molar mass of hydrogen off the periodic table from the front of your book is 14 in those last 2 digits, so plus or minus 0.00014. So we multiply that by 2, we get plus or minus 0.00028 grams per mole. For oxygen, we've got 4 oxygen atoms. The uncertainty in an oxygen atom is, as we've seen, 0.0004. So 4 times that gives us 0.0016 grams per mole. The systematic uncertainty for sulfur, we just get that off the periodic table. It's 9 in that last digit, so 0.009 grams per mole. Now we're ready to calculate the molar mass in the usual way. So 2 times the molar mass of hydrogen plus the molar mass of sulfur plus 4 times the molar mass of oxygen gives us this. And I've written down a whole bunch of digits out of my calculator, so 98.067196 grams per mole. So we're going to round this to the appropriate number in a minute once we figure out what the uncertainty is. Now we're going to propagate the uncertainties of each of these elements through our normal random error formula. That's because we might get some cancellation because there's no reason that the amount of sulfur might be connected or related to the amount of hydrogen that is present at any particular place on the planet. Okay, so those systematic uncertainties, the distribution of isotopes, there's no reason to expect that they might be connected in any way. We say that they're independent mathematically. So, all right, so we propagate them this way. So we're going to take each uncertainty, we're going to square it, we're going to add those squared uncertainties together and take the square root. When you do that, you get plus or minus 0.00915. So clearly this is dominated by the uncertainty in the molar mass of the sulfur. So that number of grams per mole. The other thing we notice is that our first uncertain digit happens here in the thousandths place. So when we go back to this molar mass, what we're going to do is round it to the thousandths place, okay? So the next digit is a 1, so we're going to round down. We're going to keep that 7, and so we'd report it as 98.067, and then our uncertainty in that number is plus or minus 0.009 grams per mole. So these 1 and 5 are not significant. We're just going to report the 9 there. And so that would be our molar mass. And so our molar mass, we know it out to 3 decimal places with some uncertainty that's this big. And then we could use this uncertainty if we were doing other calculations that had to involve molar mass, for example. Another case where you see systematic error is when you're looking at the volume delivered by a volumetric device. So for example, a Class A volumetric pipette is certified to deliver 25 milliliters plus or minus 0.03 milliliters. You can find these tolerances listed in Chapter 2 on page 32. It's table 2-4 there in the left-hand margin. And so you just look up the volume of your volumetric pipette, and then it will tell you what the tolerance is. So the manufacturer of the pipette certifies that when they sell you the pipette, that the volume will be off by as much as this, okay? No more than that. So that's the maximum error that they accept, and they call that the tolerance. So it's possible that the particular pipette that they sell you, even though it's 25 milliliters is what's written on it, it might actually be 25.003, or it might be 24.97 milliliters would be the actual volume that is delivered. So let's say we want to use this tolerance here as an estimate of the uncertainty. Well, that's a systematic error again, because your pipette, as it's manufactured, might be systematically high or systematically low compared to this 25 number. So that means the volume delivered is always in this range. So if you use the uncalibrated pipette 4 times to deliver a total of 100 milliliters, so we're going to pipette 25 milliliters 4 times to get us 100 milliliters of total volume, what's the uncertainty in the 100 milliliters that we've pipetted? Well, the uncertainty is a systematic error, and these systematic errors will add together. So the uncertainty in 4 pipette volumes is 4 times our uncertainty in the single one, 0.03. So that's plus or minus 0.12 milliliters. So if we have pipetted 100 milliliters, we might be off by as much as 12/10 of a milliliter, right? So 0.12 there. So if we were propagating uncertainty, if it were random error, we would use this formula, right? So each one of those uncertainties, we would just take it, square it, and add the squared uncertainties together, and then take the square root. That would be 0.06, which you'll see is significantly less than the uncertainty that we get by using this volume that we get by propagating the uncertainty, because we might be off by this much, depending on how close to the limits on this tolerance we are. So the difference between 25 milliliters and the actual volume, like I said, is a systematic error. But if we decide to calibrate our pipette like we learned to do in lab, then we can eliminate the systematic error, because we will then know what it delivers actually on average. So if a calibrated pipette delivers a mean volume, so we go into the lab, we measure the volume, 3 to 5 times or more, and we take the average, and so the average volume is 24.991, right? And because we've averaged those volumes together, we've done 5 trials, we can use the scatter in that data as an estimate in the random error. And so we would maybe calculate a standard deviation, and that would tell us something about the random error. So we would use this maybe as our random error. If we deliver 4 aliquots, so we use this pipette 4 times to give us 100 milliliters like we did in the second example, then the volume delivered is 4 times 24.9991, and so we didn't actually get 100 milliliters, but we know pretty precisely what we have. We have 99.964 milliliters, and the uncertainty is 0.0012 milliliters, so significantly less than what we saw before, because we've calibrated it and we've measured very precisely what the precision is by finding the standard deviation. We get this 0.0012 by using this formula for addition and subtraction, because we're adding these 4 volumes together, right? So, and then we would calculate it this way. There we go. So for an uncalibrated pipette, the uncertainty is 0.12 milliliters. So we get, look at that. 2 orders of magnitude in difference, in improvement in our uncertainty. So our precision has increased by 2 orders of magnitude because we calibrated the pipette. So here's the calibrated pipette volume down here. So we know it to 12 or 1 in this last digit here, right? Whereas with the uncalibrated pipette, our uncertainty is in the tenths place rather than the thousandths place. So that's a great way to really increase your precision in a measurement. So that wraps up Chapter 3. Let me know if you have any questions.